Greetings! In this video, I'm going to walk you through the process of solving about a medium level circuit, which means that hopefully from this video, with all the steps that I'll explain, you should be able to take these tools and apply them to not only circuits that are easier, but also maybe a little bit above the difficulty level of the one that we're about to tackle. So without further ado, let me introduce you to some of the things I have laid out here. First off, just for convenience, I've got kind of the general rule set you should think of for circuits listed out here. And remember that circuits are kind of like newspaper puzzles or Sudoku puzzles, where really you have a set of rules to follow, and you have a set of values with one starting value, through which you're supposed to apply the known values and the rules to solve for all of the remaining ones. Now, the other thing is, the circuit that we're going to be looking at here today, which is this guy down here, it's got a pretty good mix of everything. It has some things that are, thrown into the fray for us. And then finally, I have a table here just to organize all of the quantities that we've solved for and all of the ones that we still need to solve for. Lastly, I have the vocab word of the day here, which is scrunch. And really what this means is it's a term that I use for what we're about to do, which is to reduce this circuit down into a form that's as simple looking as possible, which really just means one power source and one resistor, and that's it. Which we can do using these rules by taking this big chunk of resistors right here and scrunching them down to one singular resistor. So we're going to keep this goal in mind as we find the equivalent resistance, which is going to be the resistance equivalent to all of this big chunk right here. Okay, so let's get started. So the first thing I'm going to do here, because they aren't provided, is give some labels to these resistors. And while I could give them more lengthy names, here I'm going to be boring and just label them R1, R2, R3, and R4, respectively. Alright, and now with that, we're going to begin the process of finding the equivalent resistance, which is always going to start first by scrunching the most complicated part of the circuit. So if you take a step back and look at it, you'd probably think that at the start, this pair of the 5 ohm resistor and the 10 ohm resistor are the ugliest thing currently on this circuit, which if you think that, I agree with you. So we're going to start with that. And so these two resistors are in parallel with each other, which means that we're going to be using this equation right here to find their equivalent resistance. So if we go ahead and scrunch it, what we have is a new equivalent resistance that I've called R23, which just means the resistance of the combination of resistor 2 and resistor 3. And then this equation here is kind of just a one-line version of this, because keep in mind, once you add their reciprocals, the 1 over R1 plus 1 over R2, you then have to take the reciprocal of that sum of reciprocals, which is really silly and can be annoying to put into your calculator. So here I just do that all in one line. So out of that, we should get a value of 3.33 ohms. And in case you want to keep track, this is now what our circuit looks like after we've scrunched that big blemish on the upper path. So the next most complicated thing, if we're looking at this updated circuit, is this resistor 2,3 and resistor 4 right here on the top path. And so these two resistors are in series with each other. So here, thankfully, it's nice and easy. We just take them and add them to each other directly. So we're going to go ahead and scrunch them, which now looks like this. So I've labeled this one, and I know the subscripts are getting a little crazy here, but the resistance of 234, which means the resistance of 2,3 combined with the resistance of resistor 4. I promise that's as bad as it's going to get. And so in this case, we're just adding them directly to each other. And so if we do that, Well, this one had a resistance of 3.33 ohms. This one has a resistance of 2. So we're just adding them together to get 5.33 ohms. And again, in case you're following, now our new circuit is going to look like this, which has R234 on the upper branch, and then R1 all by its lonesome on the bottom branch, in parallel with each other. So now finally, at this point, we're ready to solve for the final equivalent resistance. We have one more scrunch to do before we begin unscrunching. So, in this case, again, these two resistors are in parallel with each other. So, at this point, we are going to scrunch the final two resistors here. And so our equivalent resistance, meaning this guy right here, will equal the reciprocal of the resistance we solved for right here, plus the reciprocal of our 4 ohm resistor over here, and then we take the reciprocal of that in order to get the final resistance of this entire chunk right here, which is 2.285 ohms. And again, now our circuit looks like this. So, now that that circuit is in a nice and simple form, we may proceed to step 2, which is to start to gradually expand out, solving for currents and voltages along the way, and eventually we'll reach a point where we should have every value of voltage or current in the circuit. Alright, so I've gone ahead and cleaned our plate here, and I've started with our newly scrunched circuit down here. Now, in its current state, we have one voltage and one resistance for that voltage to pass through. So, what we're going to utilize here is Ohm's law, which, at a baseline, just states the relationship between current, voltage, and resistance. So in this case, for a given voltage and a given resistance, you would be able to solve for a current that corresponds to those two values. So in this case, we're going to be solving for the current through this branch, including the battery. So ideally, after this, we should have that value of the current in the battery. So I'm going to call this I1. And in this case, we have a voltage of 9 volts divided by our equivalent resistance here, which is 2.285 ohms. And that will equal about 3.94 amps. Okay, so it's at this point that I would like to take a step back and visualize where this current is on our little circuit map over here. So sure, we imagine that the current is traveling all the way through this little square loop here, but where is it on our overall circuit that's actually there? Well, we know for a fact that this current has to be passing through the battery. So at the very least, it has to be in the line that involves the battery itself. So what I'm doing here is I'm going to label current 1, I1, that we just solved for, by this red line on the circuit that we have. And what's happening here is charge is flowing out of the battery, and it's going to remain as I1 until it reaches our first junction right here. Now at that junction, the current is going to now split into two different options, two different paths. And so we'll have two different values that we'll have to solve for on these two branches. But at some point, when they rendezvous back up at this second junction over here, they will merge back into that original I1 over here. So, with that being said, we now have one of the values to fill in on our table. So this will be I1 equals 3.94 amps. Cool. Okay, so where do we go from here? We don't really have too much information to go off of, And so it's at this point that I recommend that you take a look at your list of rules and see what you can get out of it. And now the major thing to consider is that if we take a look at our two branches that I1 is going to split into, we can, at the very least, say that on each of these two branches, the potential across each of them has to be the same. Meaning if we're going back to our second to last circuit, where we just have a big resistor up here along the top, and then our resistor R1 down here on the middle branch, those two resistors are in parallel, and our rule sheet here states that for resistors in parallel, the potential across one branch has to be the same as the other. So across this branch, we have a voltage of 9 volts, and across this branch here, in total, we also have a voltage of 9 volts. Okay, so with that information, what we can do next is, because we know that on this branch with R1, that it's going to eat up that entire 9 volts of potential, and we know that it has a resistance of 4 ohms, we should be able to solve for the next current that we need, which I'm going to denote with a green line. And so on this green line, we'll denote this I2. And it's at this point that we have 2 of the 3 values that we need, and so this is a solvable equation. And so here, I'm going to write our work here in green, and I'll say if we want to solve for the current I2, then the voltage across resistor 1 here is 9 volts. And then we're going to divide that by its resistance, 4 ohms. And so in total, you should get a value of about 2.25 amps. So with that being said, we now have another value to go off of. And by the way, we also have some voltage across things that we can fill out here. Because we could say, well, we already said that 9 volts is going to pass across R1 conceptually due to our set of rules here. And so we could say that this branch here has 9 volts across it. And we've now just solved for the current I2 through it, which is equal to 2.25 amps. Cool. Almost there. So our next step is, well, we've been kind of putting it off this whole time, but we've got to start taking a look at this branch over here, this upper guy. And now this branch, I won't lie, has a lot more going on. So it's going to be a little tricky. We're going to have to think a little bit harder about this one, but it's okay. So within this branch, we have a conundrum, which is that 2 of our 3 resistors here have 2 different currents, both of which are not I3. So I'm going to go ahead and just draw all of our remaining currents that we need here, which is that we've got a current, I guess we'll label it I4, which is going across this top path here. And then in pink, we'll do current I5 down this bottom branch. Which runs through the 10 ohm resistor. At this point, as far as labeling goes, our circuit diagram is complete, but there's still a little bit of work to do. So, there's a couple of ways that we could go about solving this one. I'm going to summon forth one of our previously scrunched circuits. Okay, there it is. Now the reason why I'm singling out this one is because, again, keep in mind, through the middle branch here, we've got a potential of 9 volts. We already wrote down that one. And then through this branch, which in this case is all just condensed to one resistor, R234, which we had solved for as 5.33 ohms earlier. Through this branch, there should also be an overall potential of 9 volts. So, in this case, again, we have one potential and one resistance. And so through that, what we're solving for here is that blue current, I3, which is independent of all of the actual resistor craziness that's going on in that problem. So let's go ahead and get that, because that will help us take other information out of the more complicated version of the branch. So resistor I3 is going to equal, again, the 9 volts that's going across it, divided by our R234, which is 5.33 ohms. And that equals 1.69 amps. Okay, cool. So now, what we found here, if we look back at our little color-coded map, is the current that is appears to be running at the very least through resistor 4, which is the 2 ohm resistor on our chart. So we'll go ahead and put that in. That I3 for this guy equals 1.69 amps. However, this does not guarantee that the voltage across it is going to be 9 volts. Reason being, if we take a look at our rules over here, for resistors in series, which would include this chunk and resistor 4, each resistor in series has to eat up or take its share of the total amount of energy available in that branch. So resistor 4 is going to take a cut, but it has to share with this big ugly chunk right here. So the way that we can figure out the voltage across it is to say, well, hey, take a look. We need 2 out of the 3 variables in Ohm's law. Well, we have a current and we have the resistance of R4. So with these two in combination, we can use Ohm's law to figure out the total potential difference across that resistor, or how much energy it is eating up. So we'll go ahead and do that. So we'll say that the potential across resistor 4, delta V4, equals the current across it, which is I3, times the resistance of resistor 4, which is R4. And so that'll equal our current of 1.69 amps times the resistance, which is 2 ohms. And so from that, we should get about 3.38 volts. Which is how much energy resistor 4 in particular is eating up in its branch. Now note, again, that that's less than the 9 volts that's available to the whole branch. So one way that we could go about tackling this final little blemish here, the one that we've probably all been dreading, is that any remaining voltage, so the difference between 9 volts and the 3.38 that this guy's taken its share of, is going to be available to this final sector right here. So there's a couple of ways that we could think about this. The first way is by summoning forth another one of our previously scrunched circuits, which is this guy down here. So with this one, what we could look at is that, remember that 9 volts is available across the entire branch here. And so if R4 has already taken up 3.38 volts of that, whatever's left has to be available to resistor 2,3. Now, because that's applying to this combination here, another way you could have thought about it is, whatever voltage is left, that potential is going to apply across not only resistor 2 along this top branch here, but resistor 3 around this bottom branch as well. One way to think about that is that both of these resistors are effectively at the start here on top of the same hill. And by the time we reach the bottom of the hill, we should have consumed the same amount of potential energy. So all the different paths are doing here are just two different ways or two different paths to fall down the same hill, which should result in the same change in potential energy, which is all voltage is really. So what we need to do here is figure out what remaining voltage is being consumed by this whole chunk right here, which is R23 effectively. So to do that, well, we know that 9 volts is available to the whole branch, right? So we're kind of invoking this third rule here for the resistors in series. And so we know how much was eaten up by R4, and so we need to figure out how much is eaten up left by this guy here to equal the total. So the way we can do that is by saying, well, the difference between the 9 volts available minus the 3.38 volts that was eaten up already is going to equal about 5.62 volts remaining for these final two resistors here. And so the good news is that immediately knocks out 2 of the remaining spaces on our table. And so now, kind of the victory lap here, all that's left that we need to do is solve for these 2 currents, which for each resistor, the 5 and the 10, well, we have a voltage and we have a resistance, so a current is not too far behind. So since we're already using orange, we'll go ahead and solve for I4 first, the one running through the 5 ohm resistor. So say that I4 equals the voltage across it, which is 5.62 volts, divided by the resistance of it, which is 5 ohms, and so that will equal about 1.124 amps. And so last but not least, saving pink for the last and best one, I5 running through resistor 3, we could solve with voltage and resistance, or if you note that I4 and I5 have to add together to equal I3 because they split off from it. Since we have I3 and we have I4, if you subtracted I4 from I3, that should result in whatever the final current I5 is. However, I'll go ahead and just solve it here, and if you want and are curious, you can check and see. We're going to have a voltage of 5.62 volts across it, divided by a resistance of 10 ohms, which should equal 0.562 amps. And so to round it all out, I5 has to equal 0.562 amps. And that, my friends, is a complete table. So, a couple of things to note with this is, first off, organization is really important with circuits. I had the advantage of color coding and lots of space available, but really the best way to practice these things is to familiarize yourself with the rules and really get into a puzzle solving mindset. What do you have available? What tools do you have available? And how can you put all of that together to solve the next step? And while there are many ways to solve circuits, including there are tons of ways that I could have done and solved this circuit differently and still reach the same correct answer. But to start out, I think it is good practice to get used to solving a circuit through the method of scrunching and simplifying it down and then expanding things out as you're solving for those simple initial values first and using those to gradually get closer and closer to the most complicated part that we disliked seeing at the start. And so the best piece of advice I can offer is really just to look at lots of circuits, practice them, practice simple ones, practice hard ones, practice medium ones, And over time, you'll get so used to using these rules that you won't even have to think about them anymore. You'll just kind of know how to do it. It's like getting good at a game. So with that, I hope that this video helped explain some of the steps and thought processes along the way. If you enjoyed the video, please do like it, and if you have any questions, feel free to leave comments. But past that, I will see you in the next video. Peace.